Перед нами... А, нет. Я хотел сказать, что опять весь мел извели. Изверги. Нет, ничего, оставили немножко. О, все, есть, супер, спасибо. Okay, in the previous lecture we proved the so-called continuity property of the functor k0, which says that k0 commutes with inductive limits. And as a corollary, we deduced that we calculated k0 for the algebra of compact operators on an infinite dimensional Hilbert space. So we proved that this group is isomorphic to the integers. And today, our first goal will be to generalize this result and to prove the so-called stability property of k0, which says that for every C-star algebra A, if we take the tensor product of A by the algebra of compact operators, then this group is isomorphic to k0 of A. So this is called the stability. We start with the purely algebraic result, which holds for any ring, and it tells us that k0 is stable under forming the matrix ring Mn of R. So we have the following theorem. Suppose that R is any ring, as usual, not necessarily unital. And let's consider the standard embedding of R into the matrix ring Mn of R, denoted by Jn. So this map takes every element A to the matrix A plus 0. So in other words, this matrix has A in the upper left corner, and the remaining entries are 0. So I claim that this map, Jn star, Jn induces an isomorphism in K-theory. This is an isomorphism. So this result is called the matrix stability. The matrix stability of K0. Well, as the first step of the proof, let's reduce everything to the unital case. The reduction to the unital case. Well, if we have any ring R, not necessarily unital, then we can consider the unitization extension. So R is embedded into its unitization, and here we have the canonical map, a canonical homomorphism to the integers, which takes every element of this form to K. So this is a ring extension, and we can apply the functor Mn to this extension and get the respective extension of matrix rings Mn of R, Mn of R plus, and Mn of Z. And here we have the canonical inclusions, the respective inclusions Jn. So clearly the diagram commutes. And let's observe that both extensions are split. They are split extensions. Well, we know this for the unitization extension for the first line, and the second line is also split extension because Mn of R is an exact functor on a billion groups. So this is an exact sequence of a billion groups, and of course it takes retractions of rings to retractions of rings. So it is a split. It is also a split extension. And we know that the functor k0 is split exact. So after we apply k0, we get the following diagram, which contains two short exact sequences. This is the first sequence, and this is the second one. And here we have the induced maps in K-theory. So both sequences are exact. Let's denote these vertical maps by F, G, and H. And now if our theorem is true for unitary rings, then we see that G and H are isomorphisms. But if G and H are isomorphisms, then of course F is also is an isomorphism. So is F. So we have reduced everything to the unitary case. So now from now on, this is the second step of the proof. From now on we assume that R is unitary. Let's apply the functor M infinity of taking infinite matrices to this homomorphism. So we get a map from M infinity of R to M infinity of Mn of R. So this homomorphism is induced by Jn. Let's denote it by M infinity of Jn. And this ring, M infinity of Mn of R, is clearly isomorphic to M infinity of R. Let's denote the respective map by alpha. Well, an explicit formula for alpha is a bit complicated, but it's quite clear how it acts. It simply somehow removes the extra brackets. So an infinite matrix consisting of finite and binary matrices is the same thing as an infinite matrix. It's more or less clear. Okay, now let's pass to the quotients modulo the similarity. M infinity of R, quotient modulo the similarity relation. Also, we consider of course, not all ring, but a set of idempotents in M infinity of R modulo the similarity, idempotents in M infinity of Mn of R modulo the similarity, and again idempotents in M infinity of R modulo the similarity. So these two arrows induce maps here and here. So this set is nothing but K0 of R. Well, not exactly, because we have also to take the Grothendieck group. Let's also take the Grothendieck group here. So this is exactly K0 of R. This is K0 of Mn of R. And this is again K0 of R. So the first arrow here is nothing but Jn star. Jn star. And this map, well, that's denoted by, for example, by alpha tilde. What can we say about alpha tilde? Well, since alpha itself is a ring isomorphism, clearly it induces an isomorphism between idempotents, between equivalence classes of idempotents, and finally between the respective growth in D groups. So alpha tilde is a bijection. Alpha tilde is a bijection. The only thing I'd like to stress is that alpha tilde is not, in contrast to this map, alpha tilde is not induced by any homomorphism from Mn of R to R. So alpha tilde is induced by the map, which exists only at the level of infinite matrices. But nevertheless, it's a bijection. It is a bijection, and I claim that the composition of these two maps, alpha tilde and Jn star, is the identity map of K0 of R. Clearly, this would complete the proof because alpha tilde is a bijection, so this would imply that Jn star is also a bijection. Well, why is it so? Again, a formal proof of this equation is a bit tedious, so I'll just draw a picture, which I hope will be quite convincing. So indeed, for simplicity, let's assume that n equals 2. The general case is proved by a similar argument. So let's take a matrix M. Again, for convenience, let's assume that it's a 3 by 3 matrix in M infinity of R. Say A, B, C, D, E, F, G, H, I. So we apply this map M infinity and compose it with alpha. And we get a matrix in here of the following form. So how does it look like? We have to replace every entry of this matrix by the respective 2 by 2 matrix. So as a result, we get a 6 by 6 matrix of the following form. So A, B, C, D, E, F, G, H, I. And the remaining entries are 0. So this picture explains how the composition of these two maps act. So this is not the same matrix. So in other words, the composition of these two arrows is not the identity map. But on the other hand, it's rather easy to observe that this matrix is similar to M. Just use the respective transposition matrix, which interchanges the summons in the direct sum of finitely many copies of R. So this matrix is similar to M, and as a result, after we pass to the similarity classes of idempotents, we get the identity map in here. And this completes the proof. So in the general case for an arbitrary n, we can write an explicit formula, but the idea is exactly this. So we rearrange the entries by using similarity in such a way that the resulting matrix will be similar to the original matrix. Okay, let's now come back to C-star algebras. We give the following definition. Suppose that A is a C-star algebra. We define the stabilization A to be the tensor product, the C-star tensor product of A by the algebra of compact operators on a separable infinite dimensional Hilbert space. So we can either take the spatial or the minimal tensor product, or we can take the maximal tensor product here, and it doesn't matter because the algebra of compact operators is nuclear. And we say that A is stable A is stable if it is isomorphic to its stabilization. Well, the terminology hints that that the stabilization of any sister algebra is stable, and this is indeed the case. Let's recall that if we take the tensor product of two algebras of compact operators on Hilbert spaces H1 and H2, then their sister tensor product is isomorphic to the algebra of compact operators on the Hilbert tensor product of H1 and H2. So as a special case, we deduce that K tensor K is isomorphic to K because the tensor product of two separable infinite dimensional Hilbert spaces is again separable and infinite dimensional. And so if we first take the stabilization of A and then stabilize it again by using the associativity of the sister tensor product, we get the same algebra A tensor K. So the stabilization of any sister algebra is already stable. We now have the following result, theorem 2, and this is the stability of K0. So let A be any sister algebra, and let's choose a rank 1 projection P in the algebra of compact operators K. A rank 1 projection. I claim that the following star homomorphism from A to the stabilization of A tensor K, which takes every element A in our algebra to A tensor P. By the way, it's clear that this is a star homomorphism because P is a projection. So this homomorphism induces an isomorphism in K theory. An isomorphism from K0 of A to K0 of the stabilization of it. The proof is essentially a combination of theorem 1 of the matrix stability with the inductive limit argument and with the continuity of K0. So let's recall that the algebra of compact operators is isomorphic to the inductive limit, or more exactly the C-star inductive limit, of the matrix algebras Mn. So the structure maps in this inductive sequence phi ij, we know them phi ij. So phi ij acts from Mi to Mj. This is the standard embedding, which is defined whenever I is less than or equal to j. And also let's denote by phi n the canonical map from Mn to the inductive limit, that is to the algebra of compact operators. When I say canonical, I mean that it is canonical, it becomes canonical after we have chosen this isomorphism. So this isomorphism is not canonical. It depends on the choice of an orthonormal basis in our Hilbert space. But after we fixed this isomorphism, we have a canonical map from this algebra to the inductive limit, which is already in the definition of the inductive limit. Let's also recall that phi ij acts as follows. This is the standard inclusion of Mi into Mj. And phi n, well, we can choose our isomorphism in such a way that phi 1, map phi 1, which acts from C, from the complex numbers to the compact operators, takes the identity in the complex numbers to our rank 1 projection P. We have already discussed this at the previous lecture. So since the isomorphism depends on the choice of an orthonormal basis, we can choose our basis in such a way that P projects exactly on the first vector in this basis. And so phi 1 is exactly of this form. Okay, let's now take the tensor product by A. And we see that tensor product of A and K is isomorphic to the C-star inductive limit of A tensor Mn. Why is it so? Well, at the previous lecture we proved that this is true, that C-star inductive limits commute with tensor products with a maximal tensor product. But again, here all the algebras K and Mn are nuclear, and so the minimal tensor product is the same as the maximal one. So this is true because Mn and K are nuclear. So the structure maps in this inductive sequence, let's denote them by phi ija. This is just the tensor product of the identity map of A and phi ij. And phi 1, which is obtained by tensoring phi 1a, which is obtained by tensoring phi 1 by the identity map of A. So this map acts from A to A tensor K. And this is exactly the homomorphism which appears in the statement of theorem 2. So it takes every element little a to A tensor P. So we want to show that this map phi 1a is an isomorphism in K theory. We now use the continuity of the K functor of K0 and deduce that K0 of A tensor K is isomorphic to the inductive limit of K0 applied to the tensor product of A and Mn. So to complete the proof of theorem 2, we need to know that all maps in this inductive sequence are actually isomorphisms. And why is it so? Well, let's look once again at this map phi not at this map, but phi 1n, phi 1n a. So it acts from A to A tensor Mn. So this is one of the maps in this inductive sequence. Well, A tensor Mn is isomorphic to Mn of A in the obvious way. And here we have the map J and A from theorem 1. And it's almost obvious that the diagram commutes. This is just a simple calculation. Well, the diagram commutes, but we already know from theorem 1 that J and A induces an isomorphism in K theory. And so the same is true for phi 1n A. So this implies by theorem 1 that phi 1n A star is an isomorphism for every n. And now we apply the lemma from the previous lecture. Which, let's recall this lemma, it states that if you have an inductive sequence in any category, say A1, A2, A3, and so on, and if all the maps from A1 to AN are isomorphisms for every n, then the lemma states that all connecting maps in this sequence are isomorphisms, and moreover, all canonical maps to the inductive limit are also isomorphisms. So all these maps are also isomorphisms. And in particular, we see that this arrow from this object to this object is an isomorphism. So we deduce that phi 1a star, which acts from k0 of a to k0 of a tensor k, is an isomorphism. And this completes the proof. This is exactly what we wanted to show. Well, as a nice application, we can now give an equivalent definition of the functor k0 for system algebras, which doesn't involve any matrices. So, in a sense, this definition is coordinate-free. So the exercise is, if A is a system algebra, the exercise is to define a abelian semigroup structure on the set of projections in the tensor product of A by the compact operators. Well, of course, taken by the Murray von Neumann equivalence relation. Let's denote this semigroup by S. So define a semigroup structure on this set and show that the group K0A is isomorphic to the Grothendieck group of this semigroup. So in particular, if A is stable, then we just take the projections in A and factorize module the Murray von Neumann equivalence, and we get K0A. Okay, now our next goal is to introduce the functor K1 for Banach algebras, and in particular for C-star algebras. Well, let's recall that when we defined the K0, we did it in two steps. So first we defined K0 for unital rings, and then we extended this definition to the non-unital case. By contrast, there is a convenient way of defining K1 for the unital and the non-unital cases simultaneously. And towards this goal, we'll need to extend the definition of the general linear group, GLN of R, to non-unital rings. So suppose that R is a ring, as usual, not necessarily unital. So we consider the canonical map epsilon from the unitization of R to the integers. So this is a ring homomorphism, and so it induces a group homomorphism from GLN of R plus to GLN of Z. And this makes sense for any natural number n, and also for the case where n equals infinity. And we now define the group that's denoted by GLN plus of R to be the kernel of this homomorphism from GLN of the unitization to GLN of Z. So if we write this down a bit more explicitly, we see that this group consists of all matrices of the form 1 plus A, where A is an n by n matrix with the coefficients in R, not just in R plus, but actually in R, and such that the matrix 1 plus A is invertible, so it sits in GLN of R plus. So these are precisely those elements in GLN of R plus which go to the identity matrix in here, that is, belong to the kernel of this homomorphism. Of course, the identity here, by the identity, I denote the identity of the respective group, GLN of R plus. It's a simple exercise to show that actually we can replace here the unitization of R by any unital ring which contains R as a two-sided ideal. So if S is a unital ring such that R is a two-sided ideal in S, then GLN plus of R is isomorphic to the kernel of the homomorphism from GLN of S to GLN of S modulo R. Actually, this is very simple because if we look here once again at this description of GLN plus of R, it's very simple. A simple calculation shows that the invertibility of this matrix 1 plus A can be expressed entirely in terms of A. So it doesn't depend, in other words, it doesn't depend on the choice of the ambient unital ring S. Everything is expressed in terms of A. And so we have this isomorphism here. Let's look at two useful special cases of this observation. So in particular, this implies that if R is a K algebra over any commutative ring K, then we can replace the ring unitization R plus by the K algebra unitization, and we get the same result. So GLN plus of R is isomorphic to the kernel of the homomorphism from GLN applied to the K unitization, R plus K, to GLN of K. And another useful special case is the case where R is already unital. If R is unital, then we see that GLN plus of R is actually isomorphic to GLN of R. And to see this, we simply take, we simply let S equal R here. And we see that these groups are isomorphic. Explicitly, the respective isomorphism looks as follows. It takes every matrix of the form 1 plus A in here. So 1, this is the identity of GLN of R plus A in GLN of R. So this matrix goes to the identity of GLN of R plus the same matrix A. Or equivalently, we can write the following formula. We take any matrix B in GLN of R and map it to the matrix, the identity of GLN of R plus B minus 1, and here we take the identity of GLN of R. So this is the explicit formula for this isomorphism. So because of this isomorphism, we will often drop the plus sign from this notation. We adopt the following convention that very often we denote the group GLN plus of R simply by GLN of R, because it is consistent with the GLN of R in the case where R is unit. So as a result, we have extended the definition of GLN of R to non-unital rings. And let's now come back to Banach algebras. Suppose that A is now a Banach algebra. Now we say that two matrices A and B in GL infinity of A. So we have just defined GLN for any n, including the case where n equals infinity. So this is well defined. We say they are homotopic. And write the following symbol. If they are homotopic in GLN of R for a suitable n. If they are homotopic in GLN of A, sorry, for some natural n. And we define, or to use the following notation, we denote by GL infinity of A0 the set of those matrices A in GL infinity of A which are homotopic to the identity. It's a very simple exercise to show that this set is not just a set, but it is actually a normal subgroup. This is a normal subgroup of GL infinity of A. And this follows immediately from the continuity of the operations in JLN. So just take the pointwise product of the respective paths which connect the identity with two elements of in this subset, and we get a path from the identity to their product. So this is a subgroup, and the same argument shows that this subgroup is normal. And moreover, two elements A, B in GL infinity of A are homotopic if and only if they belong to the same coset modulo this subgroup. Belong to the same coset modulo GL infinity of A0. And we now define the group K1 of A to be the quotient of GL infinity of A modulo this subgroup GL infinity of A0. So as a set, it consists of homotopic classes of infinite invertible matrices in GL infinity of A. An alternative approach to K1 of A is to topologize the group GL infinity of A as follows. And this is an exercise. Let's define the canonical topology. The canonical topology on GL infinity of A to be the finest topology, making all the inclusions of GLN of A GLN of A into GL infinity of A continues. In other words, this is the respective final topology generated by the family of all such embeddings. So the exercise is to prove the following. First of all, GLN of A becomes a topological group. GL infinity of A, sorry. GL infinity of A becomes a topological group under the canonical topology. And moreover, this group is nothing but the inductive limit of the groups GLN of A in the category of topological groups. In the category of topological groups. So now if we have two elements in GL infinity of A and B, I claim that they are homotopic in the sense of this definition. Even only if they are homotopic as elements of this topological space, that is homotopic with respect to the canonical topology on GL infinity. They are homotopic with respect to the canonical topology on GL infinity way. So this can be connected by a path of elements in this group. What is essential here, I stress that, well, I don't claim that any path between A and B in this topological space belongs to GLN. I only claim that any path here is homotopic to a path which is entirely contained in GLN if n is big enough. So the equivalence relation is the same. Also, the resulting topological group GLN infinity of A is locally path connected, just like GLN of A. And our subgroup, GL infinity of A0, is nothing but the connected component of the identity, or equivalent to the path connected component of the identity. This is immediate from part 3. So as a result, we see that K1 of A as a set, K1 of A is nothing but a set of connected components by 0 of GL infinity of A. Okay, let's now observe that K1 is actually a functor. You will have a Banach algebra homomorphism. So every continuous Banach algebra homomorphism F from A to B induces a group homomorphism. Actually, it induces two group homomorphisms. First from GL infinity of A to GL infinity of B. So we just apply F to every entry of the respective matrix. And it preserves homotopy. So it takes GL infinity of A0 to GL infinity of B0. So it descends to quotients. And we get homomorphism phi F star from K1 of A to K1 of B. So we see that K1 becomes a functor from the category of Banach algebras to the category of groups. Just like K1, just like K0, sorry, is a functor. And we will see shortly that actually this functor, we will see shortly that K1 is always abelian. So again, just like K0, this functor takes our category to the category of abelian groups. Well, we will be most interested in the restriction of this functor to C-star algebras. And in the setting of C-star algebras, we can replace everywhere invertible matrices by unitary matrices, as follows. So suppose now that A is a C-star algebra. A is a C-star algebra. So if A is unital, then we denote by un of A the unitary group of the matrix algebra Mn of A. This is just a notation. And in the general case, if A is not necessarily unital, then just like in the case of GLM, we denote by un plus of A the kernel of the respective homomorphism from the unitary group un of A plus to un of C. This is just our notation. Again, for the same reason as in the case of invertible matrices, it's easy to observe that we can replace here the unitization by any unital C-star algebra, which contains A as a closed two-sided star ideal. If B is a unital C-star algebra, such that A is embedded into B as a closed two-sided star ideal, then un plus of A is isomorphic to the kernel of the homomorphism from un of B to the un of B modulo A, the quotient of B modulo A. And in particular, if A is unital, then un plus of A is isomorphic to un of A. Again, by the same formula as in the case of GLN of A. So it's natural to adopt the convention that the group un plus of A will often be denoted by just un of A. Because of this isomorphism. Now we introduce the unitary group of infinite matrices. Let's denote by U infinity of A the collection of all infinite matrices Uij, where I and j are natural numbers greater than or equal to 1, of the following form: matrices which have the following block diagonal form, where V is a finite unitary matrix in Un of A, and for some n. So we have a natural inclusion map of Un of A into U infinity of A, which takes V to B plus 1. And U infinity of A becomes a directed union, or like the inductive limit of Un of A in the category of groups. We can now define homotopy for elements in U infinity of A in exactly the same way as in GL infinity of A. Define homotopy in U infinity of A similarly to GL infinity of A. And let U infinity of A0 denote the set of those elements U in U infinity of A which are homotopic to the identity. Well, to show that this group and this subgroup leads to the same definition of K1, in the case where it is a system algebra, we need the following simple proposition, which states that U n of A is a strong deformation retract of GLN of A for every natural number n. And the proof is a simple reduction to the unital case. So we know, some time ago we proved that this is true for unital C-star algebras. So we can now restrict the deformation retraction which appeared in our proof of GLN of A plus onto UN of A plus. So we restrict it to GLN of A. So GLN of A is a subgroup in GLN of A plus. And the simple exercise is to show that this retraction takes GLN of A to UN of A and gives us what we want in this proposition. So it's a little exercise to show that this works. That is, matrices, if we take this concrete retraction, which we constructed in the unital case, and restrict it to GLN of A, then it indeed takes GLN of A to UN of A. So everything is correct. But this follows from the explicit formula for this retraction, for this retraction. So as a corollary of this proposition, we deduce that the inclusion of U infinity of A into GL infinity of A induces a group homomorphism, a group isomorphism actually. It induces an isomorphism between K1 of A and the quotient of U infinity of A modulo U infinity of A0. So in other words, we can, in the setting of C-star algebras, we can work with unitary matrices only, and this leads to the same definition of K1 of A. And again, just like in the setting of GL infinity, we can easily topologize the group U infinity of A, topologize the infinite unitary group U infinity of A, and show that K1 of A, at least as a set, is isomorphic to the set of connected components by 0 in the infinite unitary group. Okay, let's now look at some concrete examples of K1 for concrete C-star algebras. The first example is K1 of C of the complex number. To calculate this group, we need the following well-known result proposition. that the general linear group GLN of C and the unitary group UN of C are path connected. Well, this is a well-known result. It has many nice proofs. In my view, the shortest proof, probably the most elementary proof, looks as follows. We take two invertible matrices A and B. Well, actually, it's enough to consider the case of GLN of C, because we already know that this group is a strong deformation retroact of this one. So if this is path connected, then it's also path connected. So we take two invertible matrices and consider the following set S, which consists of those points lambda on the complex plane, such that lambda B plus 1, such that the matrix lambda B plus 1 minus lambda A is degenerate. The determinant is 0. And obviously this set is finite. It is finite because this is a polynomial in lambda. It is finite, so if we remove it from the complex plane, we get something path connected. C minus S is path connected. So we can choose a path from 0 to 1. A path gamma. Gamma is a path in a set from 0 to 1. And now we construct the path from A to B as follows. It takes T to gamma of T B plus 1 minus gamma of T A. And by construction, this is a path in GLN of C, which connects A and B. And that's it. So GLN of C is path connected. And the corollary, we immediately see that K1 of C, as well as K1 of the matrix algebra, and N of C is 0. Well, indeed, for K1 of C, this is immediate from our proposition. And for the matrix algebra, we simply observe that GLM of the matrix algebra Mn of C is nothing but the group of invertible matrices of order Mn, GLMN of C, and it is path connected. Well, now let's now look at something infinite dimensional. Let's look at the algebra of compact operators. K of H. Where H is any Hilbert space. Again, I claim, this is our next proposition, that the groups GLN of K of H and the unitary group U of UN of K of H are path connected. Well, here, in contrast to the finite dimensional case, it will be more convenient to consider the unitary group. Again, it's enough to consider only one of them, because this one is a strong deformation retract of this one. So we take the unitary group. So let's take an element, U, in this group, UN of K of H. K of H is not unital, so our UN is actually our UN plus by our definition. So we can write U in the form 1 plus A, where A is an n by n matrix over K of H, and U belongs to UN. This is unitary matrix over the unitization of the algebra of compact operators. So this is a unitary group of the matrix algebra Mn applied to the unitization of K of H. So this is now the sister algebra we are working in. We are working in this matrix algebra over the unitization of K of H. So what can we say about this element? Of course, it is unitary. What can we say about A? Well, A sits in this algebra, which is obviously isomorphic to the algebra of compact operators in the Hilbert space Hn. So A is a compact operator, and we know that the spectrum of any compact operator is at most countable. Sigma of A is at most countable. And of course, the same is true for U, because U is 1 plus A. The same is true for sigma of U. So U is a unitary element with an at most countable spectrum. Well, the spectrum of any unitary element is contained in the unit circle, but since it is countable, it is a proper subset of the circle. A proper subset of the circle. And therefore, we can always find a continuous function. There is a continuous function G on the spectrum of U, a continuous real valued function G, which satisfies the following equation: Z equals the exponent of I G of Z for every Z in the spectrum of U. So to construct such a function, we simply choose a suitable branch of the logarithm, which is well defined because the spectrum is not the whole circle. So we can always remove a suitable array from our complex plane and to take the suitable branch, branch of the logarithm. Well, let's now construct a path between U and the identity, which takes every point in the unit interval 0, 1 to the following element, the exponent of I T G of U. And this is a path. It's a path in Un of K of H, connecting what? If T is 0, then this is the exponent of 0, that is the identity element. So it connects the identity. And if T equals 1, the superposition property for the functional calculus, and this formula gives us that we get exactly U, connecting 1 and U. So this completes the proof. Modular little but simple exercise that this path is indeed contained in Un of K of H. This path is indeed contained in Un of K of H. Well, indeed, it's rather obvious that it is contained in here, in the unitary group Un over the unitization, because, well, G is real valued, so G of U is self-adjoint. And if we have a self-adjoint element, multiply it by I and take the exponent, we always get a unitary element. But since we're working in this algebra, we see that this is a unitary element in here. So we want this element to be contained in here. And this is a little exercise which, well, can easily be deduced from this formula, from the explicit formula for this path. So every element of this form can be written as 1, the identity matrix, plus some element over Mn of k of h. So as a corollary, we deduce that k1 of k of h is 0. Example 3. Let's now take the algebra of all bounded operators on the Hilbert space. Now let's calculate k1 of b of h. Let's introduce the following standard notation. By GL of h, we denote the group of invertibles in b of h, the group of all invertible bounded linear operators on h. And let's denote by u of h the unitary group of b of h. And again, I claim that these groups are path connected. GL of h and u of h are path connected, exactly as in the finite dimensional case. By the way, there is a deep theorem due to Kuiper, which says that if h is infinite dimensional, that these groups are also contractible. But we will need a much simpler result that they are path connected. The proof uses more or less the same idea as in the case of compact operators, but not exactly the same, because in this case, u is an arbitrary unitary operator, and of course we know that in the general case, the spectrum of a unitary operator is contained in the circle, but it can be equal to the whole circle. And in general, we cannot find a continuous function g, which is defined on the circle and has this property. But fortunately, the algebra b of h has a nice property which distinguishes it from many other C-star algebras. Namely, b of h carries the so-called Borel functional calculus. So, first of all, let's observe that there is a bounded Borel function g defined everywhere on the circle, and g is real valued such that z equals the exponent of I g of z for every z in the circle. So we simply observe that the exponent, this respective exponent is the bijection of the half interval from 0, 1. The left 0 is included and 1 is not, onto the circle. Then the inverse map is discontinuous, obviously, but it is still a Borel function. So we take this function, g, and we use the Borel functional calculus in B of H. Well, this is a standard tool in functional analysis. I'll not recall you all the details of this tool, but roughly, this functional calculus is an algebra homomorphism from the algebra of all bounded Borel functions on the spectrum of our normal. It works for any normal element of B of H, of our normal operator, to B of H, which extends the continuous functional calculus. So this tool works for B of H. In general, it doesn't work for arbitrary C-star algebras, but it works for B of H, and it gives us that for any unitary element u in U of H, g of u is a well-defined self-adjoint operator on H, and u is the exponent of I g of u. So every unitary operator can be obtained from a self-adjoint operator by this formula. And now we construct the path from u to the identity operator by the same formula as here. So we take any t from 0, 1 to the operator exponent of I t g of u. So this is a unitary operator because g of u is self-adjoint, and this is a path in U of H connecting the identity operator, and U. So we deduce that U of H is path connected, and so GL of H is also path connected. And as a corollary, we see that K1 of B of H is again 0. Well, this already follows from our proposition, because the matrix algebra Mn over B of H is nothing but the algebra of bounded operators on Hn, and so GLn of B of H is just GL of H, and it is path connected. Well, it would be nice to have an example of an algebra for which K1 is not 0. So in conclusion, let's give such an example. Example 4. Let's take the Kalkin algebra. The Kalkin algebra Q of H is by definition the quotient of B of H modulo the ideal of compact operators. Here we assume that H is an infinite dimensional separable Hilbert space. In fact, the separability assumption can be dropped, but for simplicity, let's assume that it is separable. But it is essential that it is infinite dimensional. I claim that K1 of the Kalkin algebra is isomorphic to the integers. K1 of the Kalkin algebra is isomorphic to the integers. I'll give you a sketch of a proof. Actually, the proof will be essentially a combination of well-known facts from functional analysis. Of some well-known facts which concern Fredholm operators. So let's recall that a bounded linear operator T on the Hilbert space H is Fredholm. Actually, the definition works for any linear operator between any linear vector spaces, but for our purposes, we consider operators on the Hilbert space. So it is Fredholm if its kernel and its co-kernel are finite dimensional. And the index of T is defined as follows. It is just the dimension of the kernel minus the dimension of the co-kernel. So we get map, the index map from the set of all Fredholm operators on H to the integers, which takes every operator to its index. And now let's recall some basic properties of the index. Here are some standard facts. The first fact is the set of Fredholm operators is stable under composition. So actually it's a semigroup, and the index map is a semigroup homomorphism. Index of ST is equal to the index of S plus the index of T. The second property is that the index is stable. It is indeed stable, but well, let's look at this property. So the second property is the index is stable under compact perturbations. So the index of T plus K is equal to the index of T for every compact operator K. So more exactly, the sum of a Fredholm operator and a compact operator is again Fredholm, and has the same index. Fact 3 relates Fredholm operators to the Kalkin algebra, and it tells us that a bounded linear operator T is Fredholm, even only if it is invertible modulo the compact operators. Even only if T plus K is invertible in the Kalkin algebra in QH. So we see that the quotient map from B of H onto the Kalkin algebra restricts to map from Fredholm operators to the invertibles of the Kalkin algebra, Q of H cross, a set of all invertible elements. And moreover, since the index is stable under compact perturbations, we see that it factorizes through the invertibles of the Kalkin algebra. So we get a well-defined map from here to here, which is, by the way, a group homomorphism because of 1. Property 4 is that we can further factorize this map as follows. The index is locally constant. The index is locally constant. And so it takes the connected component of the identity in the group of invertibles of the Kalkin algebra to 0. So we can take the quotient, module this subgroup, and factorize this index map through this quotient. And finally, I claim that this is an isomorphism. Why is it so? And this is true because of the following fact. Well, first of all, it's more or less obvious that it is surjective, because for any integer n, we can easily construct a Fredholm operator of index n. If n is positive, then this is the right shift by n positions with respect to a suitable, to an arbitrary orthonormal basis. And if n is negative, then we take the shift, we take the respective left shift. So it is surjective. And the injectivity of this arrow follows from the fact that fact 5, if index t, if the index of t is 0, then t can be written in the following form: s plus k, where s is invertible, and k is compact. This is the so-called Nikolsky's theorem. This formula characterizes Fredholm operators of index 0. We can now easily, by using this formula, we can easily construct a homotopy between t and s. So this implies that t is homotopic to s in the set of Fredholm operators. So simply take the path which takes t to s plus tk. So it connects t and s. But we already know that G of H is path connected, so we can further connect s to the identity operator and deduce that t is homotopic to the identity operator in the set of Fredholm operators. And this argument shows that this final map from here to here has a trivial kernel, so it is an isomorphism. So to complete the proof, we use the same matrix trick. Use the fact that Mn of B of H is isomorphic to B of H to the power n, and show that, and deduce that K1 of the Kalkin algebra is isomorphic to the integers. So because of this, everything is reduced to the invertibles modulo the connected component of the identity in here. Okay, so that's all for today. At the next lecture, we look at some properties of K1. and construct a very, very important tool, the so-called indexed map, which connects the functors k1 and k0, and which yields a very useful six-term exact sequence in k-theory. Спасибо, что приходите.